So thanks everybody for coming to the session, for the data session generally, but also for mine in particular. I much appreciate it. I'm going to talk a little bit today about anomaly detection on streaming data, which is something that I'm really interested in. I like doing streaming analytics and stuff on streams. It's fun for me. So if you are hearing and seeing the stuff that I'm saying and you think it's cool, you can tweet #Drake #hacker. That's fine. If you hearing what I'm saying and you think it's crazy and this guy doesn't know what he's talking about, #Drake thought leader. Nobody on Twitter will know what's going on, but we'll know, right? We'll know. In here, it'll be for us. So, credit to Josh Wills, by the way, for this. I thought it was funny, so I put it in the talk. So, a little bit of background on me. I studied applied mathematics years ago, but I've been interested in technology for a long time. So I actually was doing programming stuff before I went to school to study math. And the reason I studied math was because it was harder than doing programming. So it's kind of weird. I worked in a lot of startups over the years, in addition to some bigger companies as well. So I've had the experiences of building new things at growing companies and also trying to take care of big things at existing companies. Both of those come with their own challenges. And I've worked in all kinds of different industries. So I worked in financial services for 10 years. I worked in oil and gas for a while, in healthcare, e-commerce, online travel. So I've kind of had a very broad experience in terms of what I've seen over the years. Almost 20 years, I guess, doing this. Can you hear me in the back? Okay, good, great. So the idea for the talk today is about time series stuff specifically. So there's this nice, convenient, whatever you want to call it, article that time series is the new big data. I think this is from MapR. They put out a lot of stuff like this because, of course, they're trying to sell stuff to analyze the time series, but they have a point. And you also see this in the last couple of years with some of the infrastructure tooling that's come out. So has anyone here heard of like Apache Kafka, for example? A couple people, Kafka. So Apache Kafka is basically a log system, if you want to think about it that way, where you stream logging events into it. It's append only, so you just push stuff in there, and then other consumers can hook up to it and read the data back out. So each of these events is effectively a time series event. It's something that's happening temporally in some kind of order, and we won't get into ordering in distributed systems or anything like that today, but the whole big data concept movement, and I'm not a huge fan of that term, just for the record. I'm one of those data people that is a little uneasy with the term big data. Same thing for IoT. The internet is an internet of things, so I don't know why we need another term for it, but hey, I'm not the marketing guy. I'm the tech guy, so that's my side. But what I'm seeing over the last years, especially over the last, I would say, 4 to 7 years, is a lot more emphasis on time series analytics and processing abstractly instead of more the transaction processing kind of stuff that we saw in database systems in the 90s or maybe in the early 2000s. So people are thinking about this problem more generally instead of like how do we build OLAP cubes to do analytics on our sales or something like this. You're seeing systems that are coming out that are designed to process time series events. And I think this is only going to become more common. So as we get more sensors producing more streams, sending data to more places, we're going to have more advanced ways of dealing with this time series data. I don't think there's any way around it. And there's some quite cool stuff going on in the research literature. So if you want to read research papers on this, there's amazing stuff going on in compressed sensing and all kinds of ways that you can analyze this data efficiently. So we're going to talk a little bit about one kind of particular way today as an example, but there's a lot going on out there. And the problem that we're trying to solve generally. Adjust my HDMI. I can't adjust my HDMI, but I'll tell you what I can do. I can get rid of my red-shifted video. Who wants blue light in their screen? I don't. It's just my person. Okay, better? Cool. So the problem we're trying to address today is actually this one. So if you have some stream of data, some time series, whatever, you want to be able to detect when things change. And as a human, like we can look at that and say, okay, that's where it changed. It's very clear, right? But if you have 500,000 or 1 million of these different times, there's no way a human can look at it. You need a machine to do it. There's just no. You can build this nice wall of screens. Who here works in a company that has a lot of dashboards and stuff on screens? Wow, a lot of hands. How often does anyone ever use those and look at them? Never, right? Like maybe for the first couple days.
You have alerting?
You have alerting?
Yeah, you set
like Nagios or something?
Siren.
Siren, okay. And how many of those alerts have an inbox rule that goes directly to like archived?
To my garbage.
Garbage. Wow. You're brave. Okay. So as this gentleman is saying, the problem with this is there is a ton of these metrics, and there's no good way to deal with them, right? So a lot of people are doing alerting. Threshold alerting is one example we'll talk about in a little bit. But this is the problem, and it's a big problem. Especially, it's not a new one though. If you look at companies like Singtel or infrastructure providers, they've been dealing with this a long time. So it's not a terribly new thing, but it's becoming a bigger thing as we have more devices producing more streams. So this is kind of the problem. We want to identify weird stuff that happens in data streams. Everybody cool with that? Right. So there are things out there that do this, kind of, monitoring, alerting, and anomaly detection. So raise your hand if you use or have used one of these things at one of your companies. Is it graphite? Yeah? Okay. So these things are all out there, and some of them are great for different things. So like Nagios, for example, is more an alerting thing. Prometheus is kind of a metrics and monitoring thing. You have these different frameworks for anomaly detection. Breakout detection is one of them. Atlas. Skyline was one that came out of Etsy. It's in Python. It's quite interesting. No longer maintained, but we'll talk about that more in a little bit. Bosun's one from Stack Exchange. So companies are building this stuff. It's like a real problem they're trying to solve. But the issue, for example, is a lot of these are really heavy systems. It's actually a real pain to set them up. So I don't know if any of you have actually had to set up these systems, but even graphite is kind of, it's not easy. It's not easy. There are a lot of moving parts. And some of these open source anomaly detection systems are built on top of things like OpenTSDB, which requires HBase, which requires Hadoop, which requires Zookeeper, which requires HDFS. And before you know it, you have an entire infrastructure team so that you can do your anomaly detection. Like, you're laughing, but it's true. I've worked in companies where it snowballs. Somebody, usually like a well-meaning product manager, will say they want to have some kind of metrics about their product, and it spirals out of control, and sooner or later, you're building this anomaly detection system, and you have a whole like big infrastructure team supporting it. So it's a real thing, and it's a problem, because people are coupling the analytics of the time series with the anomaly detection. So they're kind of coupling the storage part, like we want to store all these time series that we've ever generated, along with the anomaly detection. You don't necessarily need to do that. If you're analyzing the stream as it's coming in, you can separate out the storage and the historical analysis from the kind of real-time anomaly detection. So decoupling those things is a good step. And we'll talk about that a little bit more. So this is an example. When I say it's heavy, I mean it's heavy, right? You probably can't see it, but that's okay because it's confusing anyway. So this is a pretty basic overview of how you would set up Graphite, which is a system that just collects metrics from your machines, from your software, whatever, and gives you some graphs, basically, about what the performance and what the behavior is like. So you have all these metrics that come in, they go into the system called Carbon Relay, which then splits them out into different clusters, that then puts them into this database called Whisper, which we'll talk about maybe in a minute about why that's problematic. And then you have some web applications in the back end and stuff so that you can actually interact with it. So just setting this up, you can imagine, is kind of problematic. The other problem is it doesn't really scale up very well at all. So in some companies, they can get by with this, and if you can, awesome. Like, don't worry about anything else because you're in a good way. But for companies that have a lot of streams or a lot of data, this system will really fall over. And when it falls, it doesn't like kind of chug along a little bit. It like really falls. It's not good. A lot of the reason being this Whisper data storage format has one file per time series. And when you start having 500,000 different time series coming in at once, just the disk activity trying to hit the files it's just not sustainable. So this is just one example, and maybe the easiest example, maybe not, but maybe the easiest example of the kind of systems you have to build if you want to solve this problem. And you want to use some of the systems that are available now. So I talked a little bit about Skyline, which was an anomaly detection system from Etsy. And you'll note this nice clean box that says Graphite, is this whole thing. So like, don't be fooled, right? Don't be fooled. So inside this box, you have all that stuff from before. Keep that in mind. And then you have Skyline, which actually does the detection of the anomalies. And as a system, the design is pretty cool. I like it. It's pretty straightforward. They don't maintain it anymore, but it's still up on GitHub if you want to look at it. And it has a few different components. It has this Horizon agent you can see that kind of takes everything in from Graphite. And it has a kind of an analyzer agent that runs through the time series and does analysis and stuff like that. And it uses Redis as an intermediate store for this data. And it has like a nice web front end that you can hook up to if you want to check some of the data out. So in theory, we're getting simpler, right? Because like this is really complicated and this looks a lot cleaner, but it's still kind of tough to get it set up. The issue with Skyline is that it also doesn't scale up. So when I was at Skyscanner, for example, we tried to use this for anomaly detection, and turning on just a fraction of the metrics from our data centers just completely killed it. It's just didn't work at all. So I started experimenting with some other ways to do this, and this is what I want. I want metrics that go into a box, and that's it. I don't want anything else. I want one executable. The Spark guy is smiling back there like, it's not distributed, but trust me, it's cool. So this is what I like, right? If you need distributed systems, they will save your world if you need them. If you don't need them and you're using them because you think it might be fun, it's not going to be fun. Like the fun is not going to outweigh the setup cost. So if you really need them, use them. Life will be good for you. If you don't need them, avoid. So this is where we want to go. We want to go from this kind of to this, which seems simpler, but it isn't, kind of down to this, which is about as simple as it gets. So the question comes up, how can we do this analysis on these streams, right? Because we don't want to store a lot of the data because that's expensive to store it. And if you have like 1 million different metrics, that starts taking up space. So really you want to start computing things as you're receiving them. So one way you could do it, don't do it, but one way you could do it is just assume that your data is normally distributed and Gaussian and all this nice stuff. Did anyone here besides Alexander study math and me? Any math people? Really? Like, you majored in mathematics? Oh, okay. That's so good. Does anyone here major in mathematics in yours? Just us. Wow, okay. So the idea here is you're computing the standard deviation of some time series, right? But you're doing it in a way that you are computing this incrementally as the values come in. So you're just getting a value, updating your mean and your standard deviation, and you're tossing it away. So the only thing you're keeping are these summary statistics. And the problem with that is you're making some extremely strong assumptions about your time series. Like really strong, like the fact that it's normally distributed, which it probably isn't. It may not even be unimodal, in the sense that it may have not one peak, but like 2 peaks, in which case this will be completely wrong. But as an example, it's quite useful. I'll show you why in a minute. So don't do it, but it's useful for our purposes now. So it will detect these point changes, like these step changes or these spikes, it will be detected. But the problem is that approach is really sensitive to outliers, which is kind of a silly thing to use if you're trying to detect outliers, because it will change your distribution. It will change the parameters. So if you have a mean that's streaming and then you have one value that spikes up really high, it's going to shift the value of the mean in a way that you don't want. But it will still work. So if I have some time, I have time? You're so captivated you're not tracking the time. No, we have another about 3 minutes, 5 minutes, right?
Right.
Okay, cool. So to give you an, wow, that's really small. Okay. That's also not working. A little better? Okay. Might work. Okay. I think for our purposes it'll do. So what I have is, and that's going to be tiny also. Okay, can't see the code too much. Oh, okay, that's better. So I did a little like mock-up in Go because I've been playing a lot with Go. recently. So this is kind of a test client that generates graphite compatible metrics. That's really all it does. It takes a random string for the metric name and a value and a timestamp. Nothing crazy. And then on the back side, I have a receiver here. Just listens on UDP for reasons that we can talk about later if you want. And it will store these metrics, compute so when it adds a metric, it will actually update the mean and the standard deviation and all that jazz as it goes. And we can do this anomaly detection in a completely streaming way. So it doesn't store any values. This is the important part. When you have super high cardinality time series data, like you have 1 million time series, right? The less you store, the more you can analyze. And if you are doing this online, then the analysis is kind of happening as the data is being received. So you don't have to have a separate thread or something that's doing the analysis. So just as a quick example, if you can see. So what I'll do is I'll start the test client with just producing normal values with like mean and normal standard mean and standard deviation. And it's like 5 metrics right now. So that's why you're seeing like maybe only 5 things. I just limited it to 5 so that you can actually see it. And you see the mean and the standard deviation are being computed. So it's numerically close to 0 and numerically close to 1. We're not keeping any values though. That's the important part to keep in mind here. So it's actually computing this as it's streaming in. So we're pretty close to where we expect to be there. If I stop the test client and make a change so that the values are now like wildly different. So I don't know if you can see it. So what I've done is I've basically changed the variance of the data to be super wide. So you're going to get a lot of outliers now. And then if I restart the test client, you'll see on the end, those arrays on the end start to fill up with anomalous data. So what we've just done is basically detect those kind of things that we said we wanted to in the first plot. So we've actually successfully solved that problem in this way. Now, you don't want to do this in practice because there are much better ways, more numerically stable and appealing ways to actually solve this time series problem. So for example, if you do it this way, your mean will shift over time. So it's actually better if you have a kind of sliding window and some kind of decay, exponential decay or something inside the sliding window. So you can keep a little bit of history, but not so much. And you also have more representative statistics for the data that is being generated. But for simple proof of concept stuff like this, it's really easy, it's really fast. You don't need all of the super heavy frameworks and stuff that are out there. You don't need, where's our nice, you don't need that to do this. It's like I think it's like 150 lines of Go code to do this. It's not a big deal. And I've tested it up to over 80,000 events a second on my laptop with a cardinality of 500,000 time series. So 500,000 distinct time series metrics, 80,000 events per second on a super old MacBook Air. So it's not that hard to do. You get tons of performance out of single machine analytics if you can do it effectively, if you can do it online. So if you don't need a cluster, don't go for the cluster. If you need the cluster, talk to this guy, he's the expert, and I'll be happy to take any questions that you have. Thank you. First.
So like I'm wondering, I mean, although we're not storing the stream, but when we have those anomalous events, we actually can store them, and it wouldn't defeat the purpose of this setup, right?
So if you were building a production system for this, you would actually want to have some kind of notification that the anomalous event happened. And what you do in that case is sort of up to you as the builder of the system. You can store it locally in memory if you want, but it's going to take up memory, and that's memory you can't use for your other metrics. So what you probably do would be to like fork off some thread or something to give the information and send an email or a notice in Slack or put it in a database or whatever you want to do in your system. Yeah. You had a question also, right?
No, it was in line with the same.
Same question. Okay. Yes.
What you do if your system actually doesn't have a single distribution? The data might be belonging to two different patterns, and it will switch from time to time.
So you're saying you have a system that generates data coming from two separate distributions depending on the time.
Yes.
And what do you do in that case in order to know that it's actually not anomalous data?
Yes,
Right.
and that you have entirely switched the distribution function.
Well, it would depend, at least a bit. My first question would be, how often does it switch? So if it's switching really, really fast, then, and those two, you could think of them as independent time series, right? You could think of them as being generated from two different distributions. And if it's switching really, really fast, you may have some mixing there that the system can handle. If it's something where every 5 days or whatever, it just goes from one distribution to a completely different distribution, then that's a different problem. I don't know if I've ever encountered anything like that in practice. Have any of you ever seen that? Has anyone seen that? No? So I've seen systems that have mixing, like you're meaning. That's usually not so hard to deal with. But in a system that goes from one distribution to some completely different distribution, I don't know if I've ever encountered that. But let's talk more about it after the session. Any? Yes.
I want to ask that what kind of database you will store?
I'm sorry, I can't hear you very well.
What kind of database I think
Database. For what?
for installing the time series?
That's the best part. I don't store them. That's one of the things that helps make it so fast.
But you want to compare over time.
Oh, like if I actually wanted to store them. Okay, so this is the question is like, how do you store these time series if you want to do analysis on them later? So this system was basically demonstrating that you don't need to combine the anomaly detection part with the historical analytics of the time series. So you can decouple those and get a lot of good performance out of the anomaly detection part, leaving the analytics off to the side. So there are a lot of systems out there that you can use for this. So it depends on how much data you have, what the time series values look like, how fast they are. A popular one is, as I mentioned, OpenTSDB. If you need it, it can be really helpful, but you're going to have to do some work to get it going. They'll tell you that you don't. So when you go to the HBase website, they'll say, oh, you can download this see, you're laughing because you know. They'll tell you can download like this standalone thing and standalone version, and it's so easy and it's so easy. And there's like a nice XML config file that doesn't look too horrible. But if you want to do it in production, it starts to get nasty. So that's one option. If you don't have a ton of data, you can just use any regular database. I mean, people frown on this now because there are so many database options, but you can get pretty far with Postgres. Like, don't underestimate Postgres. Like, it's probably a good option. But it would depend on your data volumes. It would depend on your data volumes. There are some other databases that have come out recently, like InfluxDB, which is supposed to be tuned for this. You can even write your own if you want. You can use some log structured merge tree implementation or whatever magic and build your own. If you want to do that, I don't know if that's interesting for you, but there are tons of options out there. Are you smiling because you're like never build your own time series database?
No, it's fine, but you're gonna take you about 10 years.
Yeah,
That's the given statistics for developing your own database. You need around 10 years.
Yeah, it's not trivial. So my recommendation to people for data storage, anything, is you're probably fine with Postgres. I've known some companies and I've worked at companies that aren't, but they're rare. The times where people need something besides Postgres are much fewer than the times where they want to use something fun that's new. Yeah.
For the anomaly detection, can you just run it off another machine?
Sorry?
Can it run on just another machine and pull the data of graphite?
Can what run on another machine?
Anomaly detection.
Yeah, so where's Skyline? So that's basically what Skyline does. It actually runs on a cluster of machines because the performance is a little bit problematic. But what it does is it just takes the metrics from Graphite. When they come into Graphite, you just split them off. You split off the metrics and send them to Skyline. And the system that I demoed actually takes Graphite compatible metrics. So if you wanted to, you could redirect your Graphite metrics into the demo that I built. Yeah. You wouldn't normally run it on the same machine because in a larger deployment, the Graphite has some performance challenges. So typically you wouldn't run anything else besides one of the Graphite components on that server. Yeah. Yeah.
How do you deal with time series that don't are constant in the normal case, but follows some patterns. For example, some number of views of a website, which changes over the day and changes over the weekday and is different on the weekend, for example.
So the seasonality, basically,
Yeah.
what happens when you have daily or weekly or yearly or whatever seasonality. So there are time series analysis methods you can use for this that will account for the seasonality. You can also decompose the time series into like a trend component and a seasonal component and a noise component and analyze those independently. But there are quite a few algorithms that will take care of this for you. One a lot of people use is Holt-Winters or different kinds of exponential smoothing. So it's certainly covered in the standard algorithms, and actually Graphite also has these functions built in. So if you're using Graphite, I don't know, this may be an option for you, but we can talk afterwards about particular implementations if you like. But there are many, many options.
Any more questions?
We have time, maybe one more.
Okay, I have a question.
Okay.
So like, how does this like methodology fit in with online learning, or does it ever fit in streaming analysis
So
at all?
the demo system is fully online.
Right.
It's fully online. It doesn't store any data, and every event that comes in is processed as it's received, and then it's ignored. So the demo system is fully online.
But then would
fully
it
streaming.
update the distribution itself? Or
Yeah.
That's completely up to the
No, so what it's actually doing, if you want to look it up, it's Welford's algorithm, I think, is the implementation that they use, and it's designed as a one-pass calculation of variance. You get as a byproduct of that the mean and the standard deviation. And if you have a one-pass algorithm, then you can use that as a stream processing algorithm, right? Because you can just consider one infinite pass, and then you have a stream. The problem with this is that if the distribution changes over time, you have a big issue, right? Because the values that you had in the past are not properly weighted compared to the recent history. So in reality, you wouldn't want to use this. That's why I said don't use that. You would probably have some kind of sliding window with exponential reservoir sampling or something like that, so that you can still do all of the data collection, but you're more appropriately weighting the recent data. Yeah. Did I answer your question?
Yeah.
Okay, cool. Any other questions?
Why do you think they need the distributed systems in the first place instead of going for?
Why do they? Why do
they implement this distributed systems instead of this?
So some companies really need this. I mean, there are companies out there that really need these distributed data processing systems, and for them, the pain of setting them up and maintaining them, or even building them from scratch, pales in comparison to the benefit they get from having them. Those companies are very, very few. Very few. So maybe the question you mean is, why are so many companies using these distributed systems if they don't need them? And the answer is, well, they're new and they're fun. And like Postgres has been around for 20-something years, or I don't even remember how long. And relational databases haven't been the new hotness since like the 80s. So people want to do NoSQL stuff and key value stores and all these kind of things. And distributed systems are new. They're more intellectually exciting for a lot of people. There's also some, and you're laughing, but it's true. Like I've literally been in companies where a product owner has gone to an engineering team and said, you're going to build this and you're going to use Hadoop because I need to be able to tell people that our product uses Hadoop. Because we do big data or something like this. So the reasons are almost never technical. Almost never. I shouldn't say never, because like I said, there are some companies that do really require this stuff, but they're almost never technical. Okay, I think we're out of time, but thanks very much.